Hello and welcome to Ipsa Dixit, a podcast on legal scholarship. I'm Matthew Bruckner, Associate Professor at Howard University School of Law. I'm here to talk with the authors of a new book, The Ethical Algorithm by Oxford University Press, Michael Kearns and Aaron Roth, professors of computer science at Penn. Guys, welcome to the show.
Thanks for having us.
Yeah, thank you.
So excited you guys have agreed to join. I've been trying to read more books. This is the first book I read this year. It's short. It's full of great examples. It covers a lot of ground. So I'm really excited to talk with you all today about it. In particular, I'd love to sort of talk about three things today. You cover a lot more in the book, but to talk about issues related to sort of privacy and fairness and sort of explainability of algorithmic decision making, starting in the order that you lay out in the book. So starting with privacy, I'd love for you to talk a little bit about the different sort of concepts of privacy you discuss in the book, sort of k-anonymity, differential privacy. What are these things? How do they work? What makes one type of privacy better or worse than another?
Sure. And so we sort of think of this as a great case study for the general approach we advocate in the book, which is sort of a definitions first approach. That if there's a problem and you want to solve it, the first step is to enunciate precisely and mathematically what exactly you think the problem is and what you want the solution to look like. And so when it comes to data privacy, for many years, people really didn't have definitions. They didn't bother specifying what they meant by privacy. And they sort of had this heuristic idea that, privacy could be achieved by anonymization or de-identification. So the basic idea was, if you have a collection of medical records or something, and you would like to share them with researchers so that they can learn things like that smoking is correlated with lung cancer, you could do this in a way that protected privacy by just scrubbing out from these records patient names and maybe things like social security numbers and other unique identifiers if you were careful. And what quickly became apparent is that approach by itself just doesn't work, because even though I might have removed any feature that by itself uniquely identifies you, combinations of features can pretty quickly fingerprint you. So the first public example of this was in the mid-90s. The state of Massachusetts released an anonymized collection of medical records that nevertheless contained demographic information about each patient, like zip code and gender and age. And none of these are unique identifiers, but the combination of the three of them can be. And what LaTanya Sweeney did, she was at the time, PhD student at MIT, now she's a professor at Harvard, is she realized you could cross-reference this data set with the voter registration polls of Cambridge, Massachusetts, which also had age and zip code and gender, but now connected with people's names. And she was able to figure out that you could reattach the names, and she identified the medical record of Bill Weld, the governor at the time of Massachusetts. And so, this sort of woke people up to the dangers of re-identification. And for a long time, people just tried to patch up what were seen as the flaws that were exploited in the last privacy attack. So k-anonymity was one of these attempts at patching up the problems with de-identification without really bothering to define what you meant by privacy. So the idea of k-anonymity was to say, okay, well, what LaTanya Sweeney was able to do is she was able to combine multiple features in a way that uniquely identified people. And so why don't we just try to prevent that? So k-anonymity requires that if I release a data set, I should do things like, maybe instead of releasing exact ages of patients, I'll coarsen them. So I'll just say that this patient was between 60 and 70 years old. And I'll do that in such a way so that for any collection of features that I might know about somebody, for example, that they're a 67-year-old woman who lives in a particular zip code, that any of these collections of features had better not map onto a single record in my data set, but collections of records. But it turns out, for essentially the same reason, this doesn't work either. You can cross-reference these data sets with other things about patients to once again learn things about them. And maybe it's not so surprising in that this was an attempt at patching up a broken technique, um, with an eye towards preventing a very specific attack. But since it didn't bother to specify what was meant by privacy, it's maybe not so surprising that someone more clever can come around the next day and figure out how to um, break privacy, with this band-aid as well. And so the real breakthrough in this field, and this is what we spend a lot of the time talking about in the book, is this idea known as differential privacy, which was really the first attempt to enunciate what you might want out of a privacy definition. And the basic premise is this: it says, um, imagine an idealized hypothetical world in which your data was never collected, right? So some data analysis was carried out, some data set was released, some machine learning algorithm was run. But the important thing is that in this idealized world, anything that was done was entirely independent of you because your data was never even collected. So in this idealized world, your privacy is protected, right? Your data had no influence at all on what was done. And what differential privacy asks for is that nobody should be able to tell substantially better than random guessing whether we are in the idealized world in which your privacy was perfectly protected or whether we were in the real world when your data was used. And and so the premise is if nobody can tell whether we're in the idealized world or not, and you buy that your privacy was protected in the idealized world, then maybe your privacy was protected in the real world as well.
Right, right. So the idea, right, you're promising to people that you can't sort of reverse engineer from the data that's shared publicly any one person's, data, right? You can't sort of, identify, my medical records from a data set or my, Netflix rating history because you just can't, you can't tell from the data that's released publicly, right?
And it goes beyond that, right? Like one of the problems with things like anonymity is they sort of implicitly assumed that the only privacy harm I needed to be worried about was re-identification, meaning like someone attaching my name to my entire record or something.
Mm-hmm.
But differential privacy really promises that you can't learn anything at all about me that you couldn't have learned about me without my data.
Okay. Can you talk a little bit about how we achieve differential privacy, and then perhaps I'll ask the difference between sort of this centralized and local differential privacy, but just more generally, what is a method for producing sort of differentially private information or data sets?
Yeah, so just kind of following on what Aaron said at the beginning, also about the importance of definitions. Just to be clear, the main topic of our book is really about algorithm design. It's about how if the algorithms that we use now violate social norms that we care about, like privacy, how can we fix them? How can we design algorithms that are better behaved in the first place? Mm-hmm. And so once you're armed with a definition of privacy that you feel, let's say, is the right one or an appealing one, like differential privacy, then you can move on to the algorithm design problem, which is to say, how can we design algorithms that do useful things like machine learning and AI, or just more general traditional statistical analyses, but with the promises of differential privacy. And this inevitably involves modifying the algorithms that we're used to, which generally will not automatically obey the definition of differential privacy for free from the get-go. Mm-hmm. And so in the case of differential privacy in particular, the high level idea is that you add noise to data or you add noise to computations in a way that preserves things like aggregate statistics or the models that you would build in machine learning while making promises of individual privacy. So, perhaps one of the simplest examples is just, computing the average of a list of numbers. So for instance, suppose in some large company, the company would like to, perhaps even periodically release the average salary across all 100,000 people that work for the firm. Mm-hmm. And it turns out if you just do this in the straightforward way, which is, let's say, every year, the firm on December 31st publishes the actual numerically precise average of everybody's salaries. This will not obey differential privacy. But if what the company does instead is first computes the numerically precise average of everyone's salary, but then corrupts it by a little bit of noise, by which I mean, just adding a random number to it that could be either positive or negative, that this will obey differential privacy. And the amount of noise that you would need to add to this particular statistic would depend on the number of people that work for the company. And generally, the more people there are in the data set, the less noise you need to add in order to still guarantee individual level privacy. And therefore, the estimates will be more accurate. And so this highlights another important feature of a definition like differential privacy, which is that it makes explicit the inevitable trade-off that one faces between the accuracy with which you release data or the results of computations and the amount of individual level privacy you're providing to people.
Right. And I really like that you start in the book with privacy and then move into fairness, because I think it really highlights that, this idea of differential privacy is, achievable, and depending on how much noise you want, how much protection, how large your sample is. Whereas, and we'll get to in a minute, that fairness requires, I think, as you stress in the book, even more trade-offs. And I just want to talk, though, a little bit more. Like I said, the book is pithy and full of really great examples. And I'm curious. Sometimes I feel like when I sort of write things that are a little bit shorter, sometimes I lose maybe a little bit of the nuance. And I was curious, so I came away from this book thinking like, oh, differential privacy, it's terrific, right? This seems like a good way to make use of sort of individual people's data while protecting them, and still making it still be having data still be useful. And so I was curious, though, are there sort of limitations to this approach? Right, I know you talked about sort of the need for sort of larger and larger data sets. If the more noise you're introducing to still have predictive value. Can you talk a little bit more about those sort of trade-offs between sort of I guess number of data points and the amount of noise you want to introduce in order to sort of produce both sort of useful data and still protect people's privacy?
Yeah, so there's two kinds of issues here. So the first is some tasks are just not compatible with the idea of differential privacy, even in principle. And those are tasks for which success or failure is measured according to the data of particular individuals. So if I want to learn something specifically about you, then sort of by design, it's just not something that you can do subject to the protections of differential privacy. The kinds of things that are in principle compatible with differential privacy are what I would broadly describe as statistical tasks whose success or failure is measured with respect to an entire population of people. Okay, so these are things like statistical analysis, these are things like machine learning. Now, if there's a statistical task that you'd like to do, even if it is in principle compatible with differential privacy, one thing we try to emphasize in the book is that privacy is not going to come for free. And there are inevitably trade-offs involved, not just with differential privacy, but with any reasonable notion of privacy and the accuracy of the analysis that you're going to conduct. And there's two ways to think about these trade-offs. One is that if you have a particular sort of accuracy goal in mind, so if I want to learn some predictive algorithm that's going to be able to look at demographic features of a person, maybe their sort of history of healthcare, and I want to predict their susceptibility to a disease, and I want that prediction to be accurate at least 60% of the time, for example, then if I want to be able to do that with differential privacy, I will need likely more data than I would need to be able to do that without differential privacy. So one way the cost of privacy manifests itself is in the need for more data. And if I'm in a situation where I just cannot gather more data, right, like the data set is fixed and I have to do with it whatever I'm going to do with it, then the way the cost of privacy will manifest itself is that I will have to learn a model that has higher error. And these trade-offs are inevitable. Like somehow it's fundamental to privacy that um, I'm going to have to lose some sort of statistical precision. But the nice thing about differential privacy is it provides a metric in which to sort of reason about what this inevitable trade-off is going to be. Right? So differential privacy has a parameter, right? We described differential privacy as saying there's no way to tell substantially better than random guessing whether we're in the idealized world in which your data wasn't used at all or whether we're in the real world. But what does substantially mean? Well, substantially is something we can quantify. And differential privacy as a framework doesn't take any position on how we as a society, for example, should trade off statistical accuracy with this quantifiable metric of privacy. It provides us a language and a framework in which to talk about it and in which to think about these trade-offs.
That's great. And I really like that aspect of really sort of honing in on the trade-offs that need to be made. And again, this sets up to preview sort of a contrast between, I think, sort of this fairness and accuracy trade-off. The trade-off between sort of privacy and accuracy versus in the sort of fairness context that you talk about, sort of these differential notions of fairness and how those also just compete with one another. But before we get there, I'd love to sort of talk a little bit more. So you talk about sort of like the various mechanisms by which you introduce this noise potentially into the data. One example is about sort of just having respondents in a survey sort of flip a coin, and if comes up heads, they report accurately. Comes up tails, they essentially just make something up. It's unclear whether they're speaking the truth or not. And then I think you described this as sort of local differential privacy, but you also talk about something like centralized differential privacy. And I was curious about this difference, particularly in an era where it seems like none of my data that's collected by anybody is sort of safe. That I feel like I've got 8 offers of credit monitoring because my data keeps being data breaches, and each company promises will monitor my data to sort of make up for it. So can you talk a little bit more about the different methodologies, different methods of introducing creating differentially private data sets, and this difference in particular between sort of centralized and local differential privacy?
Yeah. So the difference between those two is largely a matter of who you actually trust. So, in the case of, say, the example I gave of computing the average of a bunch of salaries, right? In that example, the hypothetical company is sort of already in possession of that data, right? They determine your salary. They have to know what your salary is already, so that they can pay it to you every month. Mm-hmm. And so they're already a centralized party is already holding your data. But you might want them, when they're releasing these averages, to do so in a differentially private manner so that the world doesn't learn what your specific salary is. Okay. And so in that case, right, you have to go ahead and trust the company when they say, well, we're going to not release the ordinary numerically precise average, but we're going to release this noisy differentially private version. Okay. There are other circumstances in which you hold your data and can decide whether to opt in to some computation or not, and might only want to do so in a differentially private fashion. And this example you were giving of what is known as randomized response in the kind of social science literature from the 60s is one example, but perhaps a more compelling recent example is in recent versions of Apple's iOS, their operating system for iPhones and other devices. So it turns out that if you've got a later model iPhone, periodically your phone reports statistics on your app usage to the mothership in Cupertino, but in a differentially private fashion. So the scenario here would be, I use my iPhone. Maybe I use different apps, and maybe I view that as kind of private information that I don't want to share even with Apple. Apple, of course, and its developers are keenly interested in app usage statistics, so they know what's popular and what's not popular. Um, and so let's say, for instance, I'm embarrassed by the fact that I still play many hours of Bejeweled every day on my phone. And so I consider that to be, embarrassing personal information. So what my phone actually does is it periodically like takes the actual usage statistics. Michael played 17.2 hours of Bejeweled this week. He looked at the New York Times for an hour and 15 minutes, etc. And as in the case of the average salary, it adds noise, but now it's going to add noise to my data specifically, and it's going to add a lot of noise. Let's say that it's going to add numbers that are much larger in magnitude than the actual usage statistics itself. So even if I played 17.2 hours of Bejeweled, it might add a random number to that usage, which inflated it to 511 hours or down even to a nonsensical value like, minus 92 hours. Mm-hmm. So huge random offsets are added to each one of my app usage statistics. And so much so that, even if we published to the world these noisy usage data for me, everybody would look at that and say, like, well, we really can't learn anything about Michael's app usage from these statistics. Mm-hmm. But if you average together the noisy Bejeweled usage statistics for 200 million iPhone users, the noise, because it's independent, basically cancels out, and you still get a very accurate underlying estimate of the underlying aggregate Bejeweled activity without learning anything about any particular person's usage. And so the great thing about this is you not only get differential privacy, but I don't even have to trust Apple to kind of treat my data in a private way, because by the time it even leaves my phone, the noise has already been added. Okay. And of course, like everything technological these days, we still have to trust Apple to have implemented this sort of local differential privacy in iOS. Mm-hmm. If we trust that, or we can, have it audited and look at the source code, etc., then we have these very strong, we have the normal guarantees of differential privacy, but we never even had to share our sensitive data with anyone in the first place. And I think, the summary is that from a practical standpoint, there are certain types of computations that we know how to do in this stronger locally differential private fashion. And there are other types of computations that we know how to do in a differentially private way, but only with like a centralized party doing the computation and everybody having to trust them to send their data in the clear to that party.
Great. Well, that's I think that's a helpful explanation, and I can't say that I in particular have great faith in who I'm sharing my data with. I also I'm also not particularly sensitive. Right? I'm still using Gmail and other apps, which I know they're sort of collecting various bits of data. Although in the book you do suggest that Google is also, I feel like Apple has a reputation for being more concerned about individuals' data privacy, but Google, I think, certainly less so. But you do mention sort of Google is also collecting certain data in a locally differential private way.
That's right. So Google was actually the first company to deploy this widely, but as perhaps will not surprise you, they didn't deploy it in their core services. So, you're absolutely right that your Android phone and Gmail are collecting lots of information about you in the clear. What they did start collecting in a differentially private way was sort of debugging information from Chrome. So Google was a leader in deploying this technology widely, but it was not, or at least has not yet been in a way that it is sort of directly relevant to what you would view as their core services.
And I would just add to that Apple can afford to be more aggressive in its privacy stances and policies and practices because they remain largely a device company, whereas Google is entirely a data monetization company. And so, stronger privacy practices encroaches on their core business more than those practices would for Apple.
So just to be clear, I'm understanding the difference. It's because Google wants to sell, or its partners want to sell me as an individual particular things. And so they need more specific information about my preferences rather than sort of aggregate preferences about law professors who live in Washington, D.C. or something.
Just generally, right? Even simply, generally, Google is in the business of, gathering very large, very diverse data sets and figuring out all kinds of services that monetize what they know about consumers. Apple sells devices, right? So it's not like data doesn't matter to Apple, but their core business is not really data. It is, selling iPhones, iPads, computers, and watches.
Right.
So
Absolutely.
these trade-offs that are sort of inevitable when you want strong privacy protections are less painful to Apple in terms of their bottom line.
Great. Thank you. So I'd like to shift a little bit now to issues related to sort of fairness, and maybe this may be more core to the book about, right, because the privacy issues, as I understand them, are sort of more about the sort of data sets, whereas fairness are now sort of more about sort of restrictions on the machine learning models that are being used. So I'd like to talk just a little bit more, in part because a lot of the sort of legal literature relating to sort of machine learning and artificial intelligence that I've read, sort of especially initially talked about the sort of bias in data, and there was some talk about the idea that sort of that using algorithms would reduce human bias, but you talk about how sort of machine learning can sort of exacerbate bias and discrimination. So can you talk a little bit about just how how we sort of measure and detect, perhaps sort of mitigate issues of sort of bias and discrimination in sort of machine learning algorithms?
Yeah, so a couple comments here. So, the way I might put it is, it's not that machine learning reduces or exacerbates human bias, but that in general, there's no reason to expect machine learning to result in anything we would call unbiased, especially in its vanilla classical form. Because in its vanilla classical form, and this is a point we make frequently in the book, machine learning is all about optimizing, and optimizing usually for some performance metric like predictive accuracy. Okay, so you have a bunch of historical data on loans that you've given and demographic properties of the recipients of those loans, maybe their social media behavior, their credit history, etc. And you'd like to use this historical data in which whether each of these individuals paid back the loan you gave them or defaulted, to build a model to predict on future applicants whether they will default or pay back. And so the very natural way of going about doing that is to say, like, well, let's fit some kind of model to this historical data that makes the most accurate predictions on the historical data that it can. And then let's go deploy it in the field and hope it makes good decisions there. And in this process that I've just described, nowhere was any notion of fairness mentioned whatsoever. It was just go for predictive accuracy. And so, in particular, if it happens to be that the most accurate, predictably accurate model exhibits racial discrimination, and what I mean by racial discrimination, I might mean something very quantitative. Like if I look at the data, the rate of false rejections, by which I mean people who actually would have repaid their loan but were rejected by the model, if the rate of that event on Black people is much higher than the rate of that on white people, then we could call this model racially discriminatory, right? And notice here a couple things are going on. First of all, since you're learning a model from historical data and real data is complicated, you're going to make mistakes. You're going to have false rejections and false acceptances. And here I've kind of implicitly identified the harm that we're worried about as being false rejections, a particular type of error. And I'm, the goal here is not to eradicate all error. That's generally impossible in machine learning. But we could ask that this particular type of error not fall disproportionately, let's say, in one racial group. And the first point I'm making here is that since I said nothing in my objective about equalizing the false rejection rates between two racial groups, I shouldn't expect it to happen. If in fact, if the machine learning process can eke out, 1/100th of a percentage more accuracy at the expense of greatly imbalanced false rejection rates between blacks and whites, it will do so because that's the most predictively accurate model. And so, this is sort of what the problem is. And then, as we do with privacy, once we identify what the problem is and suggest some definitions, then you can go about the algorithm design process and say, like, okay, if we don't want models that discriminate by race in the particular technical sense that I described, how could we alter our algorithms or the objective that those algorithms are pursuing in a way that eliminates or reduces that particular type of bias?
And just to add to that a little bit, because you bring up what is the important point, which is that people are biased too. This focus on algorithms, I think, highlights something that is different when we think about governing or regulating algorithms compared to when we think about how we should regulate human beings making the same kinds of decisions. And it's that when we've got human beings making important decisions, we sort of have this belief that it should be sufficient that the human beings involved in the decision-making process should themselves be ethical, right? They shouldn't themselves harbor any kind of, racial or gender bias, for example. And we sort of think, okay, if we have good people making the decisions, then good things will happen. Mm-hmm. One point we try to make is that it is not enough that the human beings designing the algorithms, especially if these are algorithms derived through machine learning, themselves be ethical, right? Like it would be bad, of course, if the software engineers actually were racist, but it's not enough that the software engineers not be racist, because most of the misbehavior that we see in the form of discrimination in algorithmic decision-making processes are the unintended side effects of people following the standard machine learning pipeline. So it's not enough to have to make sure, it's not enough to have ethics training and make sure that everyone involved in deploying the algorithms are themselves ethical. We actually need to understand better how to design algorithms that exhibit the behaviors that we want.
Right. Well, that's where I also thought this was an interesting chapter, especially as contrasted with the privacy chapter, because, at least as I understood it, you're suggesting that there is maybe a fairly universalizable understanding of privacy, whereas there's multiple, and I took it to be competing definitions of fairness. And by sort of specifying various definitions, you sort of highlight the need to trade them off. But is that right that there are, so you, in your example, Michael, talked about equalizing rates of false rejections, but you also mentioned that we could try to equalize, rates of false positive and other meanings of fairness. And can we optimize fairness on, 5 different, I don't know what the right word is, parameters all at the same time? Can we have equal rates of false rejections and equal rates of false positives and?
Yeah, so a couple things here. So yes, we already know, even though the study of algorithmic fairness is more nascent than that of differential privacy by maybe a decade or so, we already know that the study of fairness is going to be messier in the sense that we will always have to be entertaining multiple potentially competing or even conflicting definitions. So more on the mathematical side, you know, many definitions, most widely used definitions of fairness are of the type that I described. You first of all pick some group or attribute that you want to protect along. So you might be worried about racial discrimination or gender discrimination or age discrimination. Then you say, then you identify, well, what constitutes a harm? And maybe in lending, it's the rate of false rejections for loans. In another setting, it might be the other type of error, for example. And all of these definitions more or less have this form. You identify what group or groups you want to protect and what you want to protect them from. And then you basically say, I want to make sure that some statistic on that group isn't radically different than it is on the general population, for instance, or between the different subgroups like white loan applicants and black loan applicants. And it doesn't take much to see that if I start, since these constraints are all really constraints on simple statistics of a learned model, it doesn't take much to see that every one of these constraints or fairness conditions is like another equation in a system of equations with a limited number of variables. And so, those of your readers who remember a little bit of high school algebra will know that, if I have too many equations in too few variables, there just may not be a solution anymore, period. And this kind of thing can actually happen with these fairness definitions. And this was only realized, even though it's a rather simple observation, it was really only made in the last few years or so. But empirically, it can be even, I think, worse than that in the sense that let's take this lending example. It really could be that your data tells you that the more fairness you ask for by race, the less fairness you must have by gender. So it could really be that under the same fairness definition, which is, let's say, equalization of false rejection rates in lending, that demanding fairness by race means less fairness by gender and vice versa. And so these are hard quantitative trade-offs that really there's no answer to other than managing, right? So stakeholders / society / regulators will have to at some point weigh in and say, these are the trade-offs that are acceptable and these are the ones that are not. And there won't be any easy answers here. I mean, what easy answer can there be? Do you want more discrimination by race and less by gender, or vice versa?
Right, absolutely. I mean, our current fair lending laws require there to be, not to have these trade-offs, and so. And I guess one of the takeaways I think from their conversation, and maybe this is not right, and you correct me if I'm wrong, is that that these machine learning algorithms, which are being trained on past data and are going to sort of force these potential trade-offs between racial discrimination and sort of gender discrimination, potentially suggests to me that that this is and maybe this is maybe obviously so that. This is already what we have, that we are already discriminating against certain groups, but the scary thing about this is, I think what you're saying is, instead of machine learning fixing these problems, it's just highlighting that these problems are perhaps intractable, or trade-offs that must be made.
Yeah, I'll just make one quick comment and then I'll let Aaron jump in here. I mean, I do think that one of the consequences, but in my view, merits of the fact that we're starting to study these social norms in a quantitative scientific way with rigorous definitions and algorithmic measurement is that we might discover that our laws are actually asking for things that are unreasonable, impossible, or misguided, right? So Aaron talked about the fact that a bad definition of privacy is things like anonymity definitions, and unfortunately, HIPAA, the set of laws regarding kind of healthcare, privacy and healthcare data, they bake in an anonymity definition. So, they've taken a precise stand on what type of definition of privacy should be used, and they picked the wrong one. Similarly, to the extent that lending laws in the United States try to get at some notion of racial fairness, they basically say, oh, just don't use race as an input to your models. And this is their attempt to get at racial fairness. But in particular, forbidding the use of race in the building of models will in no way reduce the problem of racial discrimination in lending, and we go into this in the book, and it may actually make it even worse. So once again, you have a body of law that's tried to be precise. It's well intended. It's trying to be precise about a means to get at racial fairness in consumer lending, and they unfortunately got it wrong.
Thank you. And can I ask you to sort of expand on that just a little bit? Because I think that's sort of a counterintuitive point for some people. How does removing race or sort of data points associated with race, how does that potentially increase the racial bias of the sort of final models?
Good. Yeah, this is a good point, because I think it is a common initial reaction for people to say, well, if I don't want my algorithm to have any racial bias or any gender bias, I just shouldn't give it information related to race or gender. And there's 2 points to be made here. The first is that this just doesn't work even on its own terms. And the second is that, even worse, it can actually sometimes make the problem worse. So first, that this doesn't work on its own terms. Sure, I can remove race from the data, but the whole point of machine learning and statistics more generally is that it is extremely good at imputing information that wasn't explicitly in the data. So for example, if you take out race, but you have other features in there like zip code, I can come up with a very good predictor for race, and my algorithm can implicitly use these predictions for race to make decisions. So just because you've removed race doesn't remove the ability of the algorithm to make decisions as a function of race, although it can make it sort of less transparent. But the second thing is that it can be that different demographic groups have different statistical properties. So for example, one thing that is sort of frequently discovered is that when you're reading recommendation letters for, say, faculty candidates, there tends to be gender bias in the sense that letters for female candidates will, describe them more frequently using words like, diligent and conscientious, and letters for male candidates will, more frequently use, words like genius and brilliant. Mm-hmm. And if you understand this phenomenon, and you also get to see the gender of the applicants, then you can try to correct for it. You can say, okay, I know that there's this bias, for example, that manifests itself in recommendation letters for female candidates, and this is a female candidate, so I'm going to read the letter in that context. Okay, so when you have these different statistical properties for predictors that differ by demographic group, and which applicants are members of which demographic group, you can sort of correct for this differential representation in the data. But if you don't know that, right, if you've forced the algorithm to not know that by removing that information from the data set, then it prevents the algorithm from doing this correction, which the algorithm will want to do if that will serve to improve accuracy. And so you can come up with simple examples. We have one in the book where removing this demographic information can actually make things, concrete things like disparities between false positive rates worse when you then use an algorithm to solve for the most accurate model.
I think that's terrific and a really excellent point. I mean, I write about fair lending some, and I think sort of one of the assumptions underlying a lot of our fair lending laws is that racial animus is dictating differential sort of lending rates, and so therefore we try to remove a lot of this data, right? A lot, collecting data on race is often not permitted, but if it's not, racial animus, and we sort of remove this data from we don't collect this data, then I take it you're saying that we may end up with being able to, where we're going to be making, in some cases at least, making worse decisions because we don't have this data. And I think that's a really powerful point.
And I think there's two risks. I mean, first, we might be making worse decisions. That's the major risk. But the second is that it might be hard to discover that fact, right? Like if we want to audit a model, if we want to discover that it has a much higher error rate on men than women or on black people than white people, well, the data we need to audit the model depends on the demographic information of the applicants that we were trying to protect, right? We have to be able to compute the false positive rate for women or for black people, and that's difficult to do if we don't have that information. If it was not collected because its collection was prohibited by law, for example.
And is that and I mean, I take it though that you're saying that the algorithms are sort of using zip code and sort of other data points as proxies for race, and so you can't. And this is outside my zone of knowledge for sure. You can't sort of query the algorithm to try to figure out does the algorithm think this person is white or black, or you're just saying that since we don't have a sort of an objective data point, we actually just can't we can't tell whether that, so it may say, yes, I think this applicant is black, but we actually just don't know whether that's true or not.
Yeah, I mean, there's no sense in which the algorithm, or more precisely model, quote unquote, knows whether someone is black or white or male or female, if that's not one of the inputs to the model. The algorithm will just try to, the model will just try to find correlations in the whatever input variables it's given with the output that it's trying to predict, like, is this person a good lending risk or not, right?
Gotcha.
And if we remove those inputs, there won't be any explicit or even implicit way of looking inside of the black box, so to speak, and say, oh, the model has decided that this person is white or black or male or female.
Right, because it's not trying to decide.
Right, all of this is kind of in aid of our advocacy of, even though there are many, many different types of potentially competing fairness definitions, we generally believe that the good ones, rather than trying to get at fairness by constraining the inputs to a model, just instead explicitly constrain the output behavior that you want. So if you're worried about the false rejection rate in lending between black and white people being disparate, just forbid that behavior. Let the model use any input it wants. Let it use your social media behavior to decide whether to give you a loan, but just make sure it doesn't do the thing that you want to forbid. And this is, in general, I think, a much more operational definition of fairness, and also avoids the harms that can come, the active harms that can come from trying to do it the other way.
Mm-hmm. Just to echo a point we've made earlier, trying to achieve fairness, say by race, by just removing race attributes from the data, this is really, really analogous to trying to achieve privacy by removing names from the data, in that, it kind of sounds like maybe a sensible thing to do, but it avoids ever needing to enunciate what you actually meant by unfairness to begin with, right? So if, in fact, the thing that you meant by unfairness was that the model, in the end, had correlations between race and its error statistics, it made more errors on black people, then there's no reason to think that removing demographic information is going to make the thing you care about better, just as there's no reason to think that removing names is going to make the data more private if you haven't bothered to define what you mean by privacy. And so our approach here, and more generally the approach we advocate in the book, is that if you want to attack these problems in a sensible way, first you should specify what are the behaviors you want the algorithm to have, what are the behaviors you want the algorithm to not have. This can be a sort of difficult philosophical process. You have to actually make clear to yourself specifically what you meant by fairness, and that's a hard problem all on its own. But once you've done that, then you can try to achieve it. Then there's an algorithm design problem that you can tackle using all of the powerful tools of computer science.
And not to get too philosophical on this point, but needless to say, and as we admit in the book, people like us, i.e. computer scientists, AI, machine learning types, are far from the first people to have ever thought about things like privacy and fairness. Certainly legal scholars have thought about these things long and hard. Moral philosophers even longer. Economists a fair amount. But there's a special burden when you want to be so precise in your definitions that you can actually encode them in a computer algorithm. And I think one of the things we're trying to get across in our book is that there are great benefits to being forced to go through that act of precision, because sometimes by being that precise, you uncover flaws in our intuitions about these topics that you weren't going to uncover in any other way, like why is anonymity a fundamentally broken notion of privacy, and why is trying to get at fairness by forbidding the use of certain variables a fundamentally broken notion.
No, I think it's one of the things I really liked about the book. It really made me think about a lot of these issues in a different way, yeah, I think you do a great job explaining these, and particularly again through sort of easy, there's lots of examples, lots of easy to understand examples, really making your points really well. It reads so easily. It makes me think, oh, I could write a book too. But I'm sure it's what a ton of work it is to write a book that sort of reads so clearly and quickly, and come up with all these examples.
Although it was fun, I recommend writing a book.
Yeah, we enjoyed it.
Well, I know we're running out of time. I wanted to ask, though, at least briefly, about one of the issues you touch on only sort of towards the end of the book, about sort of interpretability. I think especially a lot of the legal literature, we're not computer scientists by and large, or there's a few counterexamples, so I think there was the sense, especially early, that algorithms are these sort of black boxes. They're inscrutable. They produce decisions we can't possibly understand, particularly in the fair lending context, where we require explanations for denials of credit, for example, that any sort of lender, marketplace lender, fintech lender using machine learning techniques would necessarily be unable to produce these adverse action letters. But you talk about in the book about how that an algorithm that might be in sort of inscrutable generally, sort of, I guess maybe the mechanics of it, might nevertheless produce specific decisions and individual lending decisions, for example, that we can understand, why the algorithm has said, Matt Bruckner, we're going to deny you credit. Can you talk a little bit more about that? How these models allow us to explore counterfactuals? What are the limits of these techniques?
So machine learning models are certainly inscrutable in ways that human beings are not, but the reverse is also true. These are sort of two different things. So, the reason why you can explain to me why you made a decision that you did is because, we're both human beings. We grew up, in a similar, probably cultural environment, and I sort of have a theory of mind for you. You can walk me through your decision-making process, whereas the same is not true for a neural network. I can't really understand the process by which a neural network, which might be defined by, like a vector of a million numbers, is making its decisions. On the other hand, you as a human being are very good at post hoc explanations, in that you might explain to me why you made the decision you did, but you might have come up with that explanation after the fact, right? You might not even have been aware of why you were making the decision you did, and it's really hard to say, how you would have acted in another circumstance. Whereas for a machine learning algorithm, it's a black box, but we have direct access to it. So in principle, you can ask it, okay, you denied me a loan. What would you have done on this other applicant that looks identical to me, except with these features changed? And you can do experiments for a sort of machine learning black box and just discover what it would have done in different counterfactual scenarios. So in that sense, it's easier to interrogate a machine learning algorithm. I think the way we talk about explainability in machine learning in the book is that it's obviously a very important thing. It's already mandated by law in various contexts, but it's one of these areas, maybe like privacy before the definition of differential privacy, like fairness before people tried to specify what they wanted, that it's sort of in the pre-definitional stage. So there's lots of people trying to design explainable or interpretable machine learning methods, but we haven't seen a really sort of convincing definition of what explainability really means. And it would involve pinning down, I think, explainable to whom? Like, what is the desired goal of an explanation? What are you supposed to be able to accomplish with an explanation? And so I think this is an important area, but we're not going to see real progress of the sort that we've seen in fairness and machine learning until we can really specify more precisely what an explanation is, what we want out of an explanation in technical terms.
And I think, just to add briefly to that, one of the things we do say about this topic is, we don't think that there are solid agreed upon definitions yet. And furthermore, it seems like because there's always implicitly an observer or recipient present, just the notion of explanation sort of says, like, well, who am I explaining this to? And that in particular, where machine learning is involved, the level of numeracy of that recipient might be relevant, right? So some people can handle an abstraction like a model that is mapping a set of features about an individual to a prediction, and to other people that's a very alien concept, and what would constitute a satisfying explanation to one of those might be very different than to the other. And so it also seems like a fair amount of behavioral research is needed here, just on what different types of groups of people can and cannot accept or understand as explanations for algorithmic decision making. And there's a little bit of that going on in the research community now, but I would say it's very, very early days.
Well, great, thank you. All right, well, I'm gonna try to be respectful of your time and sort of end there. So I just want to say thank you again to Michael Kearns and Aaron Roth. We've been talking about their new book, The Ethical Algorithm, by Oxford University Press. So thank you so much for your time. I really appreciate you joining me.
Thanks for having us.
Thank you.
My bathroom is a private kind of place, very special kind of place, the only place where I can stay, making faces at my face. My bathroom is my very special room, where I primp and fuss and groom, where I can get away from all and really feel in bloom. I'm free. Where I wash and where I cream.